Development of a rainfall runoff model for an ungauged location under climate change scenarios, a case study of Kabeli Khola, Nepal. Abstract. The discharge prediction at ungauged hydropower intake site is crucial thing in mountainous country like Nepal. This influences the management of generated energy corresponding to different flows in different seasons to balance between demand and supply. Among various methods available for determination of discharge at ungauged site, rainfall runoff modeling is fairly accurate over others. First, the DEM data was collected and analyzed in Arc GIS for extraction of watershed hydrological and physical parameters. Then the semi-distributed HEC-HMS rainfall runoff model was calibrated and validated taking hydrological, meteorological, climatological data as well as physical parameters in a Tamor basin, which is a gauged catchment with 2 hydrological stations at Majhitar and Mulghat. The calibration was performed for the period 1996 to 2001 and validation was conducted for period 2002 to 2006. The performance of the model was evaluated using Nash Sutcliff Efficiency, NSE, and coefficient of determination, R2. The obtained values of NSE and R2 are 0.858 and 0.8681 for Majhitar Station and 0.808 and 0.853 respectively for Mulghat Station during calibration period. Similarly, the values of NSE and R2 for validation period are 0.671 and 0.8694 for Majhitar and 0.823 and 0.8273 for Mulghat. The performance of model achieved was good and acceptable. The model with optimized parameters of the gauged catchment was then used to predict discharge at intake site of proposed Kabeli Khola Hydropower Project during calibration and validation period. 4 CMIP6 climate scenarios: ACCESS-CM2 SSP585, ACCESS-CM2 SSP245B, EC3-EARTH-SSP245B and EC3-EARTH-SSP585B. Were taken and discharge simulation was performed for the years 2015 to 2100 at same site. Similar trend was observed for maximum and minimum annual flow for 4 climate scenarios during the period. However, there is variation in annual peak flow during the period with maximum peak flow 494.9 m3/s in June 26, 2077 for EC3-EARTH-SSP585B scenario and minimum peak flow 50.9 m3/s in August 20, 2033 for ACCESS-CM2 SSP585B scenario. Mean monthly hydrographs have been plotted for calibration and validation period as well as for period 2015 to 2100 for all climate scenarios. The maximum mean monthly flow obtained was 59.9 m3/s for EC3-EARTH-SSP585B scenario. The simulated peak discharge could be utilized in the design of headworks and flood management structures at headworks site. The consistency of the energy generation from the proposed hydropower project could be assessed through the prepared hydrographs for the period 2015 to 2100. Keywords: climate projections, discharge prediction, flood management, HEC-HMS, hydrologic model, Tamor. Introduction. Nepal is one of the richest countries in the world water resources, accounting for more than 2.27% of the world's water resources, HEMS, 2015. The total hydropower potential of Nepal was assessed as 83,500 MW in 1966 by Dhruv Hari Man Shrestha during his PhD research work in former USSR, Arjat, 2011. However, various rough estimates shows that only half of this total potential is technically feasible. Nepal Electricity Authority, NEA, and Department of Electricity Department, DUED, are responsible for power development, licensing and policy making with reference to this potential within our country. The total installed generation capacity in Nepal is only 1,182 megawatts, MW, against a peak electricity demand of 1,320 MW in fiscal year 2018-2019, ADB, 2020. The reasons behind the huge hydropower potential are topography of Nepal with high relief and river with abundant water flow. Although snow-fed river in Nepal has less problem with discharge due to perennial in nature, rivers in mid-hills depend more on rainfall. Therefore, discharge prediction in such rivers plays great role as power production from runoff river hydropower schemes solely rely on river flow due to fixed head. Nepal is mountainous country and most of the gauged catchments are located at low altitudes and most of the higher altitudes catchments are ungauged. The discharge prediction of ungauged river can be made with the calibrated and validated model within the gauged river. Rainfall runoff modeling is one of the most paramount hydrological modeling that is used to investigate the relationship between the rainfall and direct runoff generated under the influence of different watershed physical parameters, Silwa and Warda, 2015 and Kisher et al., 2014. Tamor catchment with outlet at Mulghat, Dhankuta has been chosen as a study area. Tamor Basin has 2 discharge gauging stations at Majhitar and Mulghat. The calibrated and validated rainfall runoff model at this catchment could be applied for discharge prediction at the intake site of Kabeli Khola Hydropower Project, which takes supplies from Kabeli Khola of Taplajung district, Nepal. The main objective of the study is to develop rainfall runoff model for the Tamor Basin outlet at Mulghat, Dhankuta. The other specific objectives are to simulate runoff from ungauged catchment at proposed headworks point of Kabeli Khola Hydropower Project and to develop climate model to simulate future discharge data at that point. This study is believed to be useful in analyzing discharge at the intake point of the proposed headworks of Kabeli Khola Hydropower Project. The predicted discharge could be utilized in assessing efficiency of the hydropower project in hydroelectricity generation, as well as supply capacity of the project could be assessed with respect to the demand. The flood management study could be done in advance and potential future risks could be mitigated. Materials and method. The overall research methodologies adopted are described in following points. GIS data collection, processing and basin creation. DEM of Nepal of 30 m resolution has been collected and processed in Arc GIS 10.2.1 to obtain the DEM of the study area. Terrain pre-processing, watershed processing and flow path tracing has been performed for the study area using Arc Hydro tools of Arc GIS. The shapefile of Tamor Basin with outlet at Mulghat Station at Dhankuta district was thus created with number of sub-basins and stream networks. After preparing the basin, sub-basins, and stream networks with flow path tracing in Arc GIS, the project required for HEC-HMS modeling was created and generated using HEC-HMS interface in Arc GIS. The merging and the splitting of TE sub-basins created earlier was done considering the location having available flow data and location where flow data have to be simulated. There are 2 hydrological stations available within the basin, namely Mulghat and Majhitar. As basin was already cut through lower outlet point Mulghat, sub-basin has been also formed through Majhitar. Moreover, sub-basin has been also created through the proposed location of proposed headworks of Kabeli Khola Hydropower Project, where discharge data are to be simulated. Fig. 3. Tamor Basin with outlet at Mulghat Station divided into 10 sub-basins with stream networks. The basin characteristics: river length, river slope, basin slope, longest flow path, basin centroid, centroidal elevation, and centroid longest flow path were determined using characteristics tool of HEC-GEOMS interface in GIS. The land use land cover map of Nepal has been collected and extracted for the study area. The occupancy of land use type of entire sub-basins were then determined using GIS. Each sub-basins was then calculated by Thiessen polygon method in Arc GIS 10.2.1. The daily flow data observed at 2 hydrological stations, Mulghat at Dhankuta district and Majhitar at Turhadam district, have been collected from DHM for the study period. The minimum monthly value for each months for each year was then determined from the daily flow data of Mulghat station and averaged over the study period to get minimum monthly average flow value. Thus obtained flow data were then distributed to all of the sub-basins in proportion to the area of sub-basins to obtain average monthly base flow contribution from each sub-basin during the study period. The base flow calculated from daily flow data for the Mulghat station has been presented in Table 3. Table 3 shows that sub-basin 9 have minor base flow contribution of GIS map of subbasins and river network created in Arc GIS 10.2.1 was imported in Basin Model Manager interface of HEC-HMS 4.2.1. Subbasins, junctions, reaches and sinks were defined in the basin model. Downstream elements for each subbasins, junctions, and reaches were then assigned. Meteorologic model was then added in the HEC-HMS interface and prepared precipitation, flow, and PET data were given for each of the subbasins. Parameters that define the basin processing to simulate the discharge through each subbasins were then given. The parameters were set for the phenomenon like canopy, surface, loss, transform, base flow, and routing. The stream flow data are available for 11 years period from 1996 to 2006. Therefore first 6 years period from 1996 to 2001 has been chosen for calibration and remaining 5 years from 2002 to 2006 has been chosen for validation. The control specifications has been added in HEC-HMS interface and time period has been defined as chosen for calibration. The model was then run for the calibration period. The results of observed flow data and simulated flow data for both the outlet stations was compared. The discrepancy obtained between observed and simulated data shows the error in the model and the sensitive parameters affecting the runoff from the subbasins were changed till the hydrograph of observed and simulated hydrograph matched and till the performance criteria governing the efficiency of model is within acceptable range as good as possible. The calibrated model was used to simulate discharge at outlet stations for the validation period and again the simulated flows were compared with the observed flows. The performance of the model was evaluated comparing hydrographs of the simulated and observed flows as well as evaluating the values of performance criteria obtained. Flow simulation at the headworks point. The flow of Kabeli Khola at the proposed headworks point of Kabeli Khola Hydropower Project was simulated for the calibration and validation period. The RCM's data for each stations were bias corrected using Schwantile mapping method. Daily precipitation data were determined for each of the 10 subbasins using station average technique applied for the HEC-HMS model calibration and validation for the year 2015 to 2100. Similarly, daily precipitation data for each of the subbasins were determined. Potential evapotranspiration, PET, for all of the subbasins were then calculated from monthly average minimum and maximum temperature for the years 2015 and 2100 with previous humidity, sunshine hours, and wind velocity data. The calibrated and validated model was then run separately for 4 climate scenarios with new precipitation and PET data. The simulated flow at the proposed headworks point of the Kabeli Khola Hydropower Project was then obtained. Results and discussions. Model calibration. The model was calibrated for the period 1996 to 2001 using the parameters affecting the runoff through the subbasins. The different phenomenon selected that stimulate the rainfall runoff from the basin were simple canopy, simple surface, green, and amp loss, SCS unit hydrograph and Muskingum routing. These phenomenon uses different parameters for rainfall runoff response from the subbasins. Those parameters are initial storage and maximum storage for simple canopy, initial storage and maximum storage for simple surface, initial content, saturated content, suction, hydraulic conductivity and imperviousness for green and amp loss, lag time for SCS unit hydrograph and Muskingum K and Muskingum X for routing. The initial value of lag time and maximum surface storage was done based on curve number value estimated from CN grid generated from land use map and soil map. The other parameters were assumed based on the land use and soil type. These parameters were assigned to each subbasins. The most sensitive parameters were hydraulic conductivity and maximum surface storage. The model parameters were changed with a view to get maximum efficiency both manually and optimization simulation techniques. The Nash Sutcliff Efficiency, NSE, value was observed and coefficient of determination, R2, was calculated from scatter plot diagram between observed and simulated flows as presented in Figure 15 and Figure 16. Figure 13 and Figure 14 shows that there is well simulation between observed and simulated flows during the calibration period for both Majhitar and Mulghat stations. Moreover, the date of peak discharge for Majhitar station concurred for both simulated and observed data, only 3 days variation for Mulghat station. The statistical parameters Nash Sutcliff Efficiency, NSE, and coefficient of determination, R2, obtained to be 0.858 and 0.8681 for Majhitar station, and these values came to be 0.808 and 0.853 respectively for Mulghat station. This shows model performance is good during calibration period from both qualitative and quantitative analysis. However, the peak discharge obtained is underpredicted for both the stations. Model validation. The model with calibrated parameters was validated for the period 2002 to 2006 and the performance of the model was checked. The Figure 17 and Figure 18 show the hydrograph of simulated flow well coordinated with the observed flow. The Nash Sutcliff Efficiency, NSE, and coefficient of determination, R2, obtained for Majhitar station were 0.671 and 0.8694. These values were 0.823 and 0.8273 respectively for Mulghat station. These values showed the model performing in acceptable range for both stations in validation period as well. The date and time of peak flow exactly coincide for Majhitar station but variation for the Mulghat station. Likewise in calibration period, the simulated peak flow is lower than observed ones for both the stations. Annual mean flow. Figure 21 shows the graph comparing the simulated and observed annual mean flow during the period 1996 to 2006 for the Majhitar station. The graphs for both the observed and simulated data are alike with minimum flow deviation of 1.52 m3/s in the year 1996 and maximum flow deviation 85.79 m3/s in the year 2002. Similarly, the comparison of simulated and observed mean annual flow for Mulghat station for the period has been presented in Figure 22. This graph also shows harmonious relation between simulated and observed data with 172.07 m3/s, maximum, flow deviation in the year 1998 and 8.09 m3/s, minimum, flow deviation in 2005. Likewise, comparison between simulated and observed annual peak flow for Mulghat station for the period 1996 to 2006 has been presented in Figure 24 and the data have been presented in Table 7. The graph also shows similar pattern for observed and simulated data with more deviation. The maximum flow deviation is 2502 m3/s in the year 2002 and minimum flow deviation is 576.2 m3/s in the year 2006. The comparison of simulated and observed annual peak flow as well as annual mean flow data during calibration and validation period resembles the acceptable and good performance of the model during both period. The date of incident of peak discharge for calibration and validation period for the both stations are shown in Table 8. The peak discharge date coincides for Majhitar during both calibration and validation period while 3 days variation for Mulghat during calibration period and about a year variation for validation period. Although some peak discharge date variation for Mulghat during validation period, performance analysis discussed above as well as peak discharge date matching, good qualitative and statistical performance of upper altitude outlet Majhitar station suggests the developed model performed well for upper catchments. The Figure 26 shows similar values of annual mean flow at the headworks point during the calibration and validation period with maximum flow 12.75 m3/s in the year 1999 and minimum flow 8.85 m3/s in the year 2002. The Figure 27 shows that variation in annual peak flow is more or less in decreasing order with maximum value 114.60 m3/s in the year 1998 and minimum value 51.4 m3/s in the year 2006. Although annual mean flow during the period shows similar pattern, fluctuation of annual peak flow replicates the change in precipitation amount in the catchment with time. The mean monthly hydrograph has been also plotted for the calibration and validation period using average monthly flow calculated from the monthly average flow of each year. The hydrograph has been presented in Figure 28 and the flow is equal to base flow during dry seasons, January to April and October to December. Then the hydrograph starts to rise in May with peak value 39 m3/s in August and descends to meet base flow again in October. From Table X, similar values are obtained for maximum and minimum annual mean flow during the period 2015-2100 for different climate scenarios. However, Table 11 shows variation in annual peak flow during the period with maximum peak flow 494.9 m3/s in June 26, 2077 for EC3-EARTH-SSP585B scenario and minimum peak flow 50.9 m3/s in August 20, 2033 for ACCESS-CM2 SSP585B scenario. Figures 37 to 48 describe similar trend of mean monthly flow during the period 2015 to 2100 for all four climate scenarios with low flow during dry seasons and high flow during rainy season alike. Mean monthly flow hydrograph during calibration and validation period. However, it has been observed that for 6 cases of EC3-EARTH climate scenarios, from figures 43 to 48, high flows concentrated to 2 months July and August, while for other scenarios high flows seem to concentrate in August only. The maximum mean monthly flow was observed to be 59.9 m3/s and occurs in August for EC3-EARTH-SSP585B climate scenario during 2071 to 2100 period. For conclusion, river flow study has a great importance pertinent to the use of water resources for hydropower, irrigation, navigation, and many other purposes as well as river flood management. Future prediction of discharge at required section of river provides demand and supply management of electric energy as per public needs during the planning and design phase. Kabeli Khola as flow through the mountainous relief of our country has huge hydropower potential, and future discharge prediction at the proposed headworks site obviously provides some ideas in advance. The HEC-HMS model has been calibrated and validated at 2 outlet stations Majhitar and Mulghat for the period 1996-2001 and 2002 to 2006 respectively. The maximum surface storage and hydraulic conductivity are the most sensitive parameters. The statistical quantities Nash Sutcliff Efficiency, NSE, and Coefficient of Determination, R2, were evaluated to check the performance of the model during calibration and validation period. The obtained values of NSE and R2 are 0.858 and 0.8681 for Majhitar Station and 0.808 and 0.853 respectively for Mulghat Station during calibration period. Similarly, the values of NSE and R2 for validation period are 0.671 and 0.8694 for Majhitar and 0.823 and 0.8273 for Mulghat. These values are within the satisfactory and acceptable range and provided well simulation of discharge at both stations during both calibration and validation period. The developed model consists usual downside of hydrological model of under-predicting the discharge. The obtained results could be useful. The simulated maximum annual peak flow 494.4 m3/s obtained from EC3-EARTH-SSP585B climate scenarios during the period 2015 to 2100 at the proposed headworks point of Kabeli Khola Hydropower Project could be employed in planning and design of headworks structure. Similar trends observed in average monthly flow hydrographs during 2015 to 2100 period comparing with the average monthly flow hydrograph of 1996 to 2006 period for different climate scenarios might favor consistency and sustainability of hydropower in generation of electric energy for future period also. The upper catchments of Tamor Basin lie in the Himalaya region of Nepal and snowfall contributes the major portion of runoff. Therefore this study can be extended to use the snowfall parameters for developing climate model. Acknowledgement. Authors would like to thank Department of Hydrology and Meteorology, Nepal for providing hydrological and meteorological data.